So I made a bet with Calvin. If he get me a hat, I'm going to use the entire presentation.
I like the hat.
But I think it's going to be annoying. But I'm going to use, okay? If it's getting annoying, everyone, but it's a bet. I always do what I promise to do, right?
The only thing somebody, but maybe a problem, somebody may look at it and think this is a Mickey Mouse presentation.
Yeah, could be, right? Could be, could be.
You gotta sing it in the Mickey Mouse show tune, man.
Hi, Meanie. How are you, Meanie? Right? Can do something like this if you want it. So, as I told before, my name is Eduardo. I am the guy who take care of the medias in 3PAR. And one of the things about the medias is like, hey, this is the hard drive guy, right? That's what everybody thinks. But it's not like this, right? Medias are the most important thing in a storage array. You don't know it, but it is. Because you guys think, hey, is the software, is the compression, is the dedo, is the replication, is that? No, it's not. Every single evolution we have in the storage revolution was because of the media. Let's go to the first thing, right? The first storage array. Moshe and I take the SCSI drive from PC, serial channels for mainframe, put a lot of DRAM and create symmetrics. The first storage array, right? The second revolution was tiering. So we have like the 10K drives, 7.2K, and then we start doing tiering and get a lower cost GB, right? That was the first, that was the second thing. The third wave was the all-flash arrays. We see the first all-flash arrays like Violin and all of this. And this revolution started because of the media. It was not because some guy has a great idea to do a software or a different controller. It was about the media itself, right? Then we have the second generation of all-flash arrays that was about data reduction and everything, and it's where we are now. And then we go to the third wave, that is the all-flash array 3.0. That is how we're going to use the next generation media like storage plus memory, how we're going to use QLC, and how we're going to change the world again because of the medias. And because medias is the most important thing, I bring the past and the future for you guys. Look, this was the first flash we shipped in 3PAR. If you guys want to see, this is the first NVMe drive that we received from samples from Intel, like a lot of years ago to do Muse. And this is 3D Crossplay. This is the first batch of samples created by Intel. They're awesome.
No.
No, we took the chips out, so there's nothing inside of it.
No, there are chips inside, but it's not going to work for you because this unit is already.
That's all I wanted.
It's already burned out. This unit is already burned out, right? So it's not working. It's not a working demo anymore. Okay. And I'm not crazy enough to walk you around with a confidential product across the world, right? So how the media going to look like 3-4 years from now? Because that's the only thing that matters. We can talk about the software, we can talk about this. Let's talk about the real stuff, right? How is going to look like the world of the medias in the future? So the first bold statement is 10K and 15K drives are gone. They're going to be there for sure, because you still have demand, still have volume, but don't expect to see a next generation product. Don't expect to see Western Digital or Seagate releasing something incredible about hard drives, 10K and 15K hard drives. There's nothing else to be done there, okay? So basically, hard drives are going to be nearline drives. And there's a lot of innovation running in the nearline drives. They are going to be faster per gigabyte than they are today. They're going to be more dense. They're going to use crazy technologies like laser. So nearline is going to be there forever. There's a lot of use case for that, including the cloud, right? That is going to use a lot of nearline drives. And then we go to flash. So what's going to happen with flash? QLC is going to start ramping up next year and really hard in 19. But there's a very specific use case So what I expect is like 2020. Most of the storage vendors are going to start using maybe 21, and it's going to be mainstream in like 25 in petabytes shipped. And most of the demand is going to be to the very, very big cloud providers and not for a regular customer. So a regular customer cannot really use QLC in the way QLC is today because they need a very, very different approach in how to use the media. And I'm going to explain to you guys later. Okay. And then we have storage class memory. That's the bright stuff, right? So it's about 3D crosspoint and the other medias that are coming. They're totally different. There's another type of media that is showing up that is what I call low latency NAND. There's not a specific name for, but it's a flash drive that is amazing fast. Could be in some cases really close to SCM. So we are going to start calling this media as SCM, even if it's not really SCM. But in performance-wise, it's pretty close to 3D crosspoint or something like that. In some use case, not in all the cases. In some use cases, it's pretty close. Okay, so let's talk about hard drives. Just make sure that everybody understands that 10K and 50K are gone. So this is the number of units shipped in million of units. And you see it's like 12 to 14. It's shrinking a lot, the number of units. But the petabytes is still growing like crazy because of the nearline drives. Right? So let's see a little bit how 3PAR is going, right? Let's see numbers from last year, as this year we're not able to show you guys yet. Basically, if you see the growth of petabytes shipment in flash over year, like 200% in Q1 and start going down a little bit, but it's more than 150% every single quarter for us. But you start seeing the growth in hard drives and nearline drives are not happening anymore. If you think every single customer grows between 25 to 30% every year in data growth, is not going to 10K a nearline. Everything is shipping to flash, right? And then, how we're going to use storage class memory. We see 3 use cases in the future for storage class memory. The first one is to do caching. And why do caching? Because storage class memory can be an excellent replacement for DRAM. Okay? An excellent replacement. It's slower than DRAM, much lower, right? But it's still blazing fast comparing to flash.
It's bigger and more involved.
Bigger, in my opinion, the density gain for DRAM replacement in our use case in storage is not really required, right? Because when we design the controller, we have a lot of DIN slots that we can use. We can put more to get more PCI lanes. There's a lot of things involved. The density, I don't think is the big game. The big game is about cost, right? It's cheaper than DRAM. Okay, so if you think you can buy a system with X amount of DRAM, but you can like 2, 3, 4 times more using 3D crosspoint, why not use for some application that you need DRAM performance with lower costs, like metadatas, right? Metadata is the biggest thing when you go to the all-flash arrays 2.0, and the metadata could be stored in a different tier, right? So the second one is the metadata. How we can store the metadata that is responsible for like 50% of the writes in the all-flash 2.0 in a tier that is faster than flash. Because right now the metadata could be the bottleneck, and the performance when you're talking like 1 millisecond doesn't matter. But in 3PAR we're talking about 250, 300, 400 microseconds, 0.3 milliseconds. There, SCM makes a huge difference in the overall performance of the array. So metadata is a very good use case because it's below 10% of the area you use in the storage. So it makes sense financially versus a tier that would be like 20, 25%. So that's the first use case we see in the future. after caching. And then later, when become more affordable, we see as a tier of storage, a real tier of storage, right? So we go back to the hybrid all-flash array, but now it's only flash, right? And why this is so important, putting as caching? So we made a tech preview back in London in November about 3D cache, and we're going to start shipping in a couple of months. And 3D cache is using 3D crosspoint as a caching tier inside the array, and we see reductions in latency more than 50%. And the most important thing, 100% of the IOPS using 3D cache are delivered below half millisecond. So what happens usually in a regular array is that you have a very peak performance, but something like 90% of the IOPS is delivered really fast, below 500 microseconds. But the other 10% could take more than 1 millisecond in some cases. So when you see the average all-flash array, the performance is good, but you have a lot of IOPS there that happen more than 1 millisecond and can screw your performance. When you use SCM, it's exactly the opposite. You get 100% of the IOPS below 500 microseconds, and most of the IOPS running like 250. So that's the first use case of SCM, and in 3PAR is going to be in a couple of months. So in a couple of months, we're going to start shipping that functionality using 3D crosspoint. Okay, so let's separate what is hype and what is fact. And I'm only saying this because everybody talks about NVMe every single day. And it makes a lot of sense. It's a great technology, okay? But let me try to do a knowledge here. It's like buy a Porsche 911 if you live in a farm, right? You'd be awesome to have a 911. It'd be great to have a 911. But if you live in a farm, how are you going to drive fast? You're not going to drive fast, right? So that's the main thing about NVMe and NAND. That's the reason there's no hard drives using NVMe, right? And when you go to flash, look at the difference between SSD that is not NVMe, SAS drive versus NVMe drive. It's 50 microseconds, 0.05 milliseconds difference. Makes any difference for the user in the end? No, zero difference at all using NAND. What makes difference is the IOPS, right? Hey, look, the IOPS is so great. You're doing like double IOPS versus a SAS drive. Doesn't matter either, because when you buy a storage array, you're not buying 2 drives. You're buying 16 drives, 24 drives. And the controller is going to be the bottleneck, not the drive itself. So the hype about NVMe that everybody says all the time makes a lot of difference for a server using 1 drive or 2 drives, but makes no difference at all in a storage array running 16, 24, 32 drives, because the controller is the bottleneck, right? And the 50 microseconds difference in latency that you can get maybe wash away with all the software compression dedupe you have inside the storage array. But when you start talking about storage class memory, this 50 microseconds make all the difference. 120 microseconds in NVMe flash versus 30 microseconds for SCM. If you take 30 microseconds and you add more 5 microseconds, it's almost 50% increase. So it makes no sense to use SAS for storage class memory. So with the right media, NVMe is perfect. For flash, in the storage array, it makes no difference. And let's understand a little bit about smaller systems, right? When you talk about NVMe, all the vendors that start talking about NVMe, they say, hey, look how great it is, right? With like 8 drives, 10 drives, I can give you 100% of the performance, right? That's the main thing. Very dense. First, if you're buying a system with 10 drives, you have like half of the slots empty. So there's no density gain, right? Because you're still using the space. 10 drives make no difference. If you're using the full 2U array or 3U array and all the drives, the performance will make no difference because you're using like 20, 24 drives, and the NVMe advantage goes away because you're using the number of drives, and the controller is going to be the bottleneck. But what makes a lot of difference is the overhead. And nobody talks about this. Nobody, right? So let's make clear. If you buy a system from other all-flash vendors with like 10 drives, the overhead of double parity, metadata, spare area, you be something like 47%. So if you're buying 100 terabytes, it's going to be in the end 53 only. And then you add dedupe and compression and maybe go to 200, but you lose like 47% of every single NAND chip on with metadata and overhead with 10 drives. If you buy a 3-part with 8 drives, that is the smallest system that we sell. We can sell with 6, but we always recommend 8. It's 37.5%. It's already lower. Yeah.
Now, that's if you're treating it in a traditional rate methodology, but if it's erasure coding based, etc., that doesn't necessarily apply, does it?
To be honest, all these all-flash array vendors that are using erasure code and everything, their overhead is around 40-something%. Okay, for all of them. So if you look, most of them is this, and that's another use case that has a very, very small overhead, but you need to buy 25 drives each time, and they have something like 13% overhead. But what they do, they have a lot of overhead inside the drive. So let me give you an example of this vendor, right? They use a 1.6 terabyte drive, and we use exactly the same drive, but we give you 192 terabyte in the same drive. So the hardware of the drive, like I show you guys, is exactly the same, but they put 20% more overhead inside the drive to handle their overhead and the wear out and all that stuff they need to do, like garbage collection inside the drive. In 3-part, for example, we decide to give you a very small overhead in the drive itself to give you more usable capacity, and you use a little more in the overhead of the system. So we are like 18%, our best use case like 1875, and for this vendor is like 13%, but they use 20% more in the drive itself. So for them, you're going to be like 33 in the end, right? So we are the system with less overhead in the entire industry. And we can say this with proud because in the end, you're buying flash, you're paying for raw flash, and that makes a lot of difference, right? So let's just continue here and you guys understand again. So in the end, why does it matter, right? If you're buying a system with 8 drives, the $GB would be like $640, right? But if you're buying 16 drives, because the lower overhead that we can provide when you add more drives is going to be $492. So this is like 20% cheaper per GB. The other flash vendors, they're like flat in 40-something. So if you're buying 8 drives or 30 drives, you're going to put an overhead in you guys for like 40-something%. Okay? So that makes a lot of difference. And when you talk about NVMe getting worse, right? Let me explain to you guys. NVMe drives are at least 20 to 25% more expensive per gigabyte because it's a new technology, it's premium. They're just one vendor that is really doing NVMe dual-ported drives. So they're charging more for that. So in the end, when you compare a system with 16 drives, SAS drives, and you look the $GB, it's 4.9. If you get the system with double capacity using only 8 drives, it's going to be 7.7. It's like 45% more expensive by a dense NVMe system versus buying the right, perfect SAS system with exactly the same performance. So NVMe is going to be the future. We're doing NVMe prototypes since 2014, and it's going to be the future for sure. But right now, there's no economics. We need to wait economics be there to start really using massive. Because today, customer want the technology that is fast, simple to use, and cheap, right? Right? If you have simple to use and has a great performance but don't have the economics, customers will not buy, right? How many customers want 50 microseconds difference in the latency of the array? Okay, there will be a lot. There's 3D crosspoint. Then they're going to give you like 200 microseconds difference in your latency, not 50, just because you're using NVMe flash, right? So that's the main point for us about what is hype and what is reality about NVMe. How many minutes I have?
15.
Okay, I'm doing fast.
15,
Okay.
but we can go a little bit over.
No, I think we can finish in 15
So
and
actually-
open a lot of questions.
Go back one.
Sure.
That's the slide. Chris Evans sent a tweet and asked, he said, I thought the SAS NVMe would be a bigger cost differential. What's the IOPS difference on the comparison chart?
The IOPS difference, in this case, IOPS particular is going to be pretty close. In the 8 drives, it's going to be faster in NVMe, like 25% faster. With 16 drives, you'll be none. There'll be zero difference in IOPS between SAS and NVMe. It'll be a latency benefit of about 50 microseconds, but it's going to be between 20 to 25% more premium in the system. And because today there's only one array that is full NVMe shipping, they're charging like 60% more, right? But that's about the media side. They're putting a premium because they are ahead in that use case, so they're putting premium, but it's the media itself costs between like 25% more expensive. Okay? So if you buy a drive or a server that is SAS versus a drive in a server using NVMe, it's going to be 25% premium. Okay, Chris? Yeah, sure.
A comparison that shows the IOP differences?
It's not showing the IOPS difference here, but I can guarantee for you after 16 drives, exactly the same. Below 16 drives makes a difference. Okay? After 16 drives, no difference at all. No difference at all. And how many systems we sell with less than 16 drives? Almost none. Because the overhead is the payout. That's the biggest problem. So when you go to a customer, let me give an example. You go exactly this, right? And you say, hey, I want 128 terabytes. I can sell 128 terabytes for you using the 1536 and 8 drives, right? I can do it. I put 8 drives of 1536. If I take the same system and put 16768, the dollar gigabyte usable, not raw, usable is going to be like 11% cheaper. Okay? The raw is going to be like 4% higher, but the overhead, remember, 37% versus 18%, it's half the overhead. So what I always recommend to everybody in the field, if you're doing a system with 8 drives, take that drive, split in the middle, and put 16. It's going to be cheaper in the end, the dollar gigabyte usable. It's going to be cheaper because the overhead is smaller. And that's the main thing. People are thinking they are selling the biggest drive. They're saving you money. It's the opposite. Because the overhead is going to be bigger. That's the main thing. It's like doing RAID 6, 6 plus 2, versus do RAID 6, 14 plus 2, right? Easy math. That's exactly what I'm doing here. RAID 6, 6 plus 2 versus RAID 6, 14 plus 2. Okay? That's the benefit. So you lose 2 extra drives between the 8 and 16. Okay? I answer you?
Kind of.
Please rephrase for me.
Well, I was just kind of curious, like, what the performance differences are, like, you know, cost for I/O versus capacity.
Okay. Dollar IOPS.
For IOPS?
Yes.
Dollar IOPS is going to be pretty close. Pretty close. But you're going to have less usable space.
Well, and does dollar $IOPS also fall with response time and latency response time?
Response time is exactly it's
It's
50
the same.
microseconds.
Okay,
It's 50 microseconds. It's none.
so that's a level.
It's washout, right?
Mhm.
50 microseconds washout. If you're talking like 500, you go to 200. That's something, right? You go to 450 to 500, washout, right?
Right.
So the main thing about NVMe is like you can do a system that can perform higher with the same number of drives and to a certain limit. And what we have seen in all our tests is 16 drives. And to 16 drives, it's a big advantage over NVMe, but you get 16 drives and over exactly the same, right? And the other thing about NVMe that you guys need to worry about it's NVMe. It's pretty complex. SAS is pretty mature, and right now it's so easy for us, right? We're doing SAS for 10 years. When you talk about NVMe, you cannot scale, so you need to do a dense system. You cannot do a system with like 200 drives. Okay, so there's much more complex to do NVMe than is to do SAS.
Although, what about some of the people positioning NVMe fabric-based and tending to, not necessarily 200 drives, but more than just a standard shelf or so?
Fabric definitely is the future. Definitely is the future, right? But as every single technology needs to be mature, and that's the main thing about storage, right? You buy storage array because you want to sleep at night, right? If you don't want to sleep at night, you're going to do your own storage device, buying servers, drives, and you're going to do your own stack, right? You buy storage array because you want to sleep at night. So we introduce technologies when they are mature enough in a lot of ways. So the NVMe over Fabric right now, they just closed the standard and it's not really finalized yet. There's a lot of discussions. So pretty basic stuff like hot swap drives is not really defined. So imagine what is more important than you fail a drive, you're going to remove the drive from the system and put a new drive. There's something more basic in this, and it's not really defined in the NVMe over Fabric standards yet. Right? So there's a long path there, but it'll be the future for sure. So everything that you see today as a SAS fabric, SAS backend, is going to be NVMe in the future for sure. In 2020, definitely.
The other thing to bear in mind is that you're talking about performance being gated by the controllers is predicated on a 2 or 4 controller architecture, not a scale-out architecture.
Yes.
The performance metrics or performance scaling changes completely when you go to a scale-out controller architecture.
Yes, but let's put that in another perspective, right? There's all the architectures that we have today, even 3-part with multi-controller nodes, right? The number of drives that we put in a single entity that we call node pair, it's smaller, right? It's not like I put 100 drives and the 8 controllers talk with the 100 drives at the same time, right? So like every 2 controllers are going to talk with some drives, and every single architecture that we have today in the market talks like that, right? When you go to NVMe over Fabric in the future, you are going to be able to do that, but it'd be a long path because we need other stuff like SRIOV, and there's a lot of standards that is not there yet. But the future is going to be something like you're saying. You're going to have a bunch of drives and a lot of controllers in the right architecture. You're going to be accessing the same drives at the same time, right? But when this happens,
not necessarily access the same drives.
That's what I expect from the future. Right?
That's a nice feature from the NVMe fabric.
But that's the biggest advantage, right? It's sharing drives, sharing data. This is NVMe over Fabric. It's breaking through barriers that we have with the SCSI, Fiber Channel, or SAS. That's the main thing about NVMe. Everybody talk about the latency, that you can direct connect the cores to the drive. That's not the breakthrough stuff for me. The breakthrough stuff is like you can really share the drives. That's kind of unique. Okay, I'm going to talk a little bit about this in the end, even just a few more slides. Okay, so how we're going to do with 3D cache, right? How we're going to use this great Intel card inside our controller to give something that is what customer want, right? Faster, better, cheaper, right? How we're going to do this? We're going to move from like what we do today, a system with like 128 drives, to a system that has only 32 drives and 3D cache in the front with the same capacity, give it higher performance, lower latency, and lower price. So look the IOPS GB, right? In all the three use cases, like you asked me before, right? So if you use the right media with NVMe, makes a lot of sense. But if you're using NAND versus NAND, don't make sense. You're just paying higher for nothing, right? You're just paying higher. So this is the right use case for NVMe. You get a card with a different type of media that is 15 times faster than NAND, 20% lower latency, and you make a benefit in the end. I'm selling you for you the same system, the same capacity, higher performance, lower price. That's what we should do in the industry, right? Do something better and cheaper. So how about QLC? Everybody knows here what is QLC? Everybody understand how the technology works, why it's different?
I don't really understand QLC, so if you don't mind explaining quickly.
I'm going to try to do like very simple because it's very complex.
Yep.
So basically 3D NAND is 3 bits per cell, right? QLC is 4 bits per cell. Okay? So that's the first thing. So you get 25% more capacity in the same piece of die. Okay? But QLC already starting with some crazy number of layers. So we're going to start with 64 layers in a piece of die, and pretty soon it's going to be 128. Pretty soon. Okay? And it scales really, really well. Different than SCM or all that stuff that don't scale that well, QLC scales like crazy. You can go easily to 500 layers in the future without any like huge architecture change. So that's the main thing about QLC. But there's a lot of trade-offs, right? There's a lot of trade-offs. The first trade-off of QLC is the performance for writes. The performance for writes, it's terrible. It's terrible. It's like between 50 to 100 times is lower than regular 3D NAND. Okay? But for reads, it's as good as 3D NAND. So if you take like the high-end Intel Samsung 3D and you take a QLC and do reads, it's really close. But when you do writes, terrible. Terrible. Okay? If you're doing random writes, if you're doing sequential writes, it's as good as 3D NAND. And that's the main thing, right? So you're going to need a lot of architecture chains in the storage arrays to make sure they can write for this media sequentially, like Nimble does with nearline drives, right? We do that with Nimble today using nearline drives. So QLC needs like the same behave, how you write the media, right?
So Eduardo, what would be one of the good use cases of QLC media?
Everywhere. I'm going to give you a use case in the next slide, okay? The QLC, you're going to start seeing a lot of adoption with all this cloud providers that do their own stack, like Google, Amazon, Azure. Those guys are going to change their stack to do extreme writes, right? And you're going to start using like day one. Because they can change their stack. Because they know their application, right? For us, it's harder because I really need to, I don't know what kind of workload the customer is going to put inside the system, right? So we create a system that can run everything. I don't create a system that runs like, hey, this is good for Exchange server, right? This is good for SQL server. I do a system that can run everything together. So I need to behave the media in the software stack, and I take care of the media for you. It's not the opposite, right? And QLC needs a lot of care. It's like a baby, right? You need to take care of like 24 by 7, right? You need to really take care of it. It's exactly the same when we started using SSDs like 7, 8 years ago, right? It was something very unique. 8 years from then, like 2009 to now, SSD is easy for us. It's going to be the same in the future with QLC. Exactly the same. So you have a long path to start using that media. And I think it's going to be really, really fast. 2020, 21, when economics makes sense, we're going to start using a lot. And I think in like 24, 25, the shipments in terabytes in QLC is going to be bigger than 3D, right? Oh, sorry, that one. So how are we going to use QLC, right? Think on that. Think on that today. This is the system we sell today. 24 drives, 16 terabyte drives using 3D NAND. That's what we ship today, right? How is going to be the first generation QLC that's going to showing up now in the end of this year, beginning of next year? And we do exactly the same system using 33% of 3D NAND and 67% using QLC. We're going to see a cost difference of like 2 or 3%. So it don't make sense to use the first generation QLC because the economics are not there. I need to handle with a lot of stuff for like 2, 3%. Don't make sense. So we're not going to use the first generation. We're going to wait for the second generation QLC. Then you're going to start seeing a lot of increase in the density and more cost reductions. And then we are going to use a hybrid flash. That you're going to have 3D for most of your writes, QLC for most of your reads, and SCM for your metadata. So the next generation 3PAR, we're going to use the 3 types of media for different things. So metadata will be like SCM, 3D NAND is going to be for very, very intensive writes, and QLC is going to be for streaming writes and a lot of reads. Okay? And why? How many minutes? 5? Okay. Last one. Why architectures matters, right? And this is what changes everything. If you think in the scale-up platform that you have dual controller, right? Most of these architectures are like dual controller, one active and the other is passive, right? Your bottleneck is simple. It's one control. Because the other one is standby, right? You can, like, some architectures share a little bit of things like front end port, but the back end is just a single controller, especially when you have compression dedo. So the bottleneck is that single controller. And even Intel do a great job bringing new CPUs every 18 months. You cannot keep it up with the speed of storage plus memory and the next generation needs. So if you want a system that you don't want to do like a mini IOPS, that architecture would be great for you, right? Then you have the second architecture that is the scale-out platforms, right? And there are people in the room using one scale-out architectures in the back. I'm not going to say names. I'm not saying the shirt is red, but that is a scale-out architecture, right? That, you know, you can...
Socks, by the way.
Sorry, man, it's just a joke. Don't be mad.
There's anything wrong.
So basically, all these scale-out architectures that you have compute and drives together, you have a huge problem that all these nodes interconnect. You need a switch, right? And every time you put a switch in the middle, you're losing something. So saying, hey, yeah, but you have an InfiniBand switch, and you can do 25 microseconds latency. When you talk about a media that can do 10 to 12 microseconds, and you add 20 microseconds latency in the network, you just wash out SCM. You just destroy SCM in the architecture itself, right? But when you go to an architecture like we have in 3PAR, that is a scale up and a scale out, right? That you can add more nodes or you can add more drive shelves in the same node. And all the nodes talk with each other using an ASIC, using PCI lane between them with less than 1 microseconds latency between the nodes. You can take advantage of the next generation media And that's the reason we are introducing 3D crosspoint in our systems today, because we're ready for this type of media. All the other architectures, if they put 3D crosspoint there, you make no difference. You make no difference in the system level. But for us, it makes a lot of difference because you can really leverage the speed of the media in the cluster. That's why architectures matter, right? That's it, guys. I'm done. Drop the mic. Right?
Hey, before we go, any questions before we move off the topic?
Yeah, so Chris on Twitter had mentioned, he says, is it better to create scalable file object platform for that type of requirement? Because before that, he had mentioned that if the growth data is unstructured, it doesn't make sense to use a three-part architecture with QLC. And then he said, the better to create a scalable file object platform for that type of requirement.
Yeah, but that's the point, right? People are thinking about QLC to use for objective store. QLC is going to be our regular drive in the future. So right now, if you look at QLC, saying, hey, this is a bad drive. It's a slow drive. No, it's not. The drive, the read performance of QLC is as good as 3D TLC, right? It's amazing fast. But what you really need to care of is how you're going to write in that media, right? And we are going to do this. This is what storage industry is famous for. You take the cheapest drive available and make it great, right? That's how we started storage industry with Moshe and I 35 years ago, right? We take the consumer PC drive and you create a symmetrics. It's going to be the same with QLC. You're not going to use QLC for object storage. For object storage, you're going to use nearline drives, right? Nearline drives with a tier of flash for caching. That's where it's going to be object storage in the future, because you don't want to store in the future 1 petabyte. You want to store like 1 exabyte, and QLC will be too expensive for you.
So what I'm thinking is what you're saying is you're going to use the cache to kind of store the memory, the data, temporarily, and then as it takes the QLC the time to actually write that data,
yes.
So it kind of becomes like a buffer layer.
No, it's not. If you're thinking like Nimble architectures, is that what they do with Flash and Nearline today? But that's Nimble architecture. So Nimble can introduce QLC like this. If they want, they can do like this and put QLC there because it's ready for, right? In our case, in 3-part, what we're going to do, it's all the systems will have 3D NAND. So most of the writes are going to happen in the 3D tier. And with the tiering technology, we're going to move from the 3D tier to the QLC tier. If you look at 3-part array today, 90% of the IOPS are done in like 85% of the capacity. Sorry, in 15% of the capacity. So 85% of the capacity of the array are doing like 10% of the IOPS. This is like mandatory to go to QLC. And QLC is a great technology. It's not like bad quality media, like a lot of vendors are trying to say. It's not. And it was just one vendor talking about this 2 years ago. Now all the vendors are talking about QLC because they know they miss it, right? And now everybody's crazy to do QLC. Even the #1 vendor of NAND was like, no, QLC is bad, QLC is bad. Now he's just released a QLC product in Flash Memory Summit, right? So QLC is there. QLC is the future of NAND for most of your data, not most of your workloads. The workloads we are going to treat for you inside our array. Okay?
Yeah, Eduardo, I'm not real current on 3-part, but it used to be.
You should be. You should be.
I should be. That's totally my fault. Thank you.
I'm going to fix that.
Thank you.
We have all day. We have all day.
But as I recall, the number of nodes that you can interconnect is like 8 nodes.
Because not because there's a limit. Right, let me try to explain to you. So we have an ASIC today in our generation that have a number of PCI lanes in that ASIC.
Right.
We dedicate one PCI lane for each other controller to interconnect. So if I have a controller here, and I want to connect that controller to more 7 controllers like we do, we need 7 PCI lanes dedicated for that interconnect, right?
Right.
We do that today because we don't want to put a switch like the 27 ladders now. It was 3, now it's 27. I don't know. And what HDS does in the XP that put the switch in the middle. You want to do direct connect because nothing can be faster than this, right? And so in the ASIC that we have today, we need to put 2 ASICs to do the 8 controller. We can take the same controller and put 4 ASICs and do 16 controllers, right? We can do it today if you want it. We don't do it because we don't see a use case for it. We don't see customers buying 60 nodes, 32 nodes. That doesn't mean that we are not ready to do it. We just need to put more ASICs in the board, right? So if the future wants 32 controllers, we can do it. The architecture was ready since day 1 to do it, okay? So right now we do 8. We can do more if we want. Give me a customer that's going to buy $1 billion in storage. I give you 128. I'd be happy to. Okay, so it's not an architecture limitation; it's a business decision change.
Right.
Okay.
And so your ability to use SCM is based on the fact that the interconnect is PCIe between the nodes, and the latency that you see with PCIe is
Below than 1 microsecond. Below than 1 microsecond, right? Versus a switch, even if you put an infinite band switch, it's like 12, 15, 20, right? And you need to have at least 2, so you need to do round robin, so you wait CPU cycles to do it. So there's a lot of things over there that we don't have it because we are PCI lane connect each other. That's the beauty of our system.
there is a PCIe switch. Have you looked at that?
So there's a PCI switch inside every single server in the world, right? You have to have a PCI switch because you have several lanes. So it's required to have a PCI switch there. And we have a PCI switch inside there. And we use to do this interconnect, right? But there's no latency at all, just like pre-wiring. Totally different than switch. Then like InfiniBand switch, a protocol switch, right? This is like controller-to-controller connection using no emulation, no protocols. It's just PCI. That's the beauty.